So in the last section, we were talking about polyprotic acids, and we said a polyprotic acid has more than one acidic hydrogen. So when we calculate pH and H+ concentrations for polyprotic acids, it's going to look a little bit different. Now, here we've got our example. We've got phosphoric acid. We've got a 5 molar solution. And then it says that we want to determine the pH as well as the concentration of phosphoric acid, H2PO4-, HPO4 2-, and PO3 3- at equilibrium. So here's the way we're going to do this. I'm going to start with the phosphoric acid. In water, it's going to break up into H+ and H2PO4 -1. Okay? Now, if I look at the table for phosphoric acid, I know that the first Ka is 7.5 times 10 to the negative third. I know that that's equal to the concentration of my products, which I don't know, so I'm going to say both of those are x. So x times x is x squared, over the concentration of my reactants. Now remember, at equilibrium, we say that this is going to change so little that we can ignore the change. I had 5.0 molar of that. So I'm going to solve for x. So I'm going to multiply both sides by 5. And then I'm going to take the square root. So when I do that, I get that x is going to be equal to 0.194. Okay? Now, over here, remember, I had 5.0 molar initially of this, 0 of this, 0 of this. It's going to change. So that's where those x's came from. Now, what I'm saying is that 5 minus 0.194 will give me the equilibrium concentration of H3PO4. So that gives me 0.48. I said that my H+ concentration is 0.194. And my H2PO4 concentration at equilibrium is 0.194. Okay? Now, I'm going to have the second H come off, the third H come off, but they're going to happen to such a very small extent that I can actually calculate my pH based simply off of this here. And the reason I'm going to do that, 10 to the negative third, 10 to the negative 8th, 10 to the negative 13, these second and third H are going to come off to such a small extent compared to the first. I'm just going to ignore that for pH. So I'm going to say that the pH is equal to the negative log of my H+ concentration, which I said was 0.194. So my pH is going to be equal to 7.2. Okay, so that gave me my concentration at equilibrium of H3PO4, and it gave me my concentration, oops, sorry, not that one, this one, H2PO4. It also gave me my pH, but I still need the concentration of HPO4 2- and PO4 3-. So I'm going to need to do another calculation. I know that my H2PO4- in water is going to break into H, and I know that it's going to break into HPO4 2-. Okay? Now, initially, I've got 0.1 0.194 of this. I got that from the calculation above. Initially, I've got 0.194 of this. I want to find out about this, okay? So that I don't know. Now, if I look at my table, I'm going to look at my Ka2 because this is the second H coming off. So I know that 6.2 times 10 to the negative 8th is equal to the concentration of my products, so 0.194 times X divided by the concentration of my reactants, 0.194. Dividing anything by itself, it cancels out. So I'm told that X is going to be 6.2 times 10 to the negative 8th. So my HPO4 is going to be 6.2 times 10 to the negative 8th. Okay? So now I have H3PO4, H2PO4, HPO4. Take a second and solve for PO4 3 minus. So you're going to have HPO4 2 minus breaking into PO4 3 minus and H plus. You know your initial concentration of HPO4 2 minus. We just calculated it in the last problem. We know the concentration of H plus. We calculated it in the first problem. And use your Ka3, which is 4.8 times 10 to the negative 13th. So sometimes we have things dissolve in water that don't look like acids or bases. Now, if I dissolve a salt in water, sometimes it'll affect the pH. A salt is going to be an ionic compound. So remember, we've got a metal plus a nonmetal. When the salt dissolves, it's going to break into ions. Okay? Now, generally, our cations, our positively charged ions, will usually be acidic. Anions will usually be basic. Not always, usually. Now here are some exceptions, okay? If we have a strong acid, remember we said a strong acid breaks apart completely. So the conjugate base of a strong acid will not affect the pH. So for example, HCl breaks into H plus. What I care about is the Cl minus. Cl minus is not capable of picking up an H and going backwards. So Cl minus will never affect our pH. If it has a Br minus, it will never affect our pH. An I minus will never affect our pH. I'm going to go back to this one because it's a little bit different. Nitrate, perchlorate, and chlorate. None of those ions will affect our pH. Conjugate bases of a strong acid. Remember, we also had the strong bases. So any of our alkali metals, so Na plus, Li plus, blah, 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 all the way down, none of those will affect our pH. Same thing with alkaline earth. But remember, when we looked at our base, it wasn't all of the alkaline earth that were strong base. It was starting at calcium down, okay? So those won't affect our pH, okay? Now, H2SO4 is a little bit different. the reason that H2SO4 is different is even though it's a strong acid, it's also a polyprotic acid. So my H2SO4 is going to break apart completely into H plus and HSO4 minus. However, HSO4 minus is a weak acid. It can break apart into SO4 2 minus. So if I have SO4 minus in solution, it's a weak acid. It'll break apart. This will make my solution acidic. If I have SO4 2 minus in solution, it can still pick up an H to reform HSO4. So this will make the solution basic. So all of the other strong acids and strong bases, the conjugate bases, conjugate acids, don't mess with our pH. But sulfuric acid, that one's unique and that one's different, so you'll need to remember that. Okay? So remember, salts that contain the conjugate base of a weak acid will make the solution basic. Salts that contain the conjugate acid of a weak base will make the solution acidic. Okay, so vice versa.